Welcome everyone to the seminar from the QT Center for Robotics. I'm Thierry Penot. I'm associate professor here at QT, member of the Center for Robotics, and I'm also the vice chair for IEEE Queensland Robotics and Automation Society and the Joint Control Systems Society. And it's in those two capacities I'm have the great pleasure to host this seminar and to introduce my good friend Teresa, who we have the pleasure to have on the seminar today, calling from Sydney. So the seminar will be entirely online today. Teresa, well, I've known Teresa for a while now, since around 15 years, I think. So,
oh man, you don't say these things.
Say a few things about her, but that could be a long list. I'm not going to do a long introduction, but Teresa did her PhD in Erie in Barcelona, which is one of the top robotics lab in Spain. She then went to do a postdoc at LAS, my old lab where I knew her. Obviously top robotics lab in France. Afterwards, she went to do a postdoc at ACFR, which was the top robotics lab in Australia at the time. I just followed the pattern. And after that, she joined UTS, where she became a senior lecturer and deputy head of school at the moment as well. Teresa has a lot of experience with robotic perception in general, including, of course, SLAM, localization mapping, data fusion, pattern recognition, and also action based on perception for ground robot, aerial robot, etc. So a whole variety of background. And as I mentioned to the group today, she has very strong theoretical background with very strong application in the real world. So I'm really looking forward to see some really good stuff from here. And her talk is on continuous and probabilistic models for integration, localization, mapping, and planning. And without further ado, please, Teresa, take it away.
Yep. Thank you, Thierry, for the introduction. Yes, Thierry mentioned we met a long time ago, actually, in LAS, when he was leaving, so and I was just joining the center. But anyway, yeah, thanks for the introduction, Thierry. I'm talking today about three of our very recent work. A lot of continuous and probabilistic models, as you'll see. So first, I'm gonna do a quick presentation, very quick about our center. For the ones who don't know, the Center for Autonomous Systems in UTS, which now is in this year at some point it's going to change name. We're going to be a robotics institute, the UTS Robotics Institute. But well, the same people continue working on that, and we include more people from inside UTS. And then, well, I'll start talking about the continuous and probabilistic models that I want to talk to you today. So the center, so we are around 80 people, 80 plus, with 10 academic staff, around 20 postdocs and research engineers, and roughly 50 PhD students, well, PhD and master students, mostly PhD. Some of these students come, 35% of these students come from our undergrad programs. So we teach the mechanical and mechatronics undergrad. And we also have a master's in robotics that just started, and we teach around 500 plus students. So our research income comes mainly from industry. We get around 5 million external income from collaboration with the industry. So one of our projects, the most famous projects, and I'm not gonna put the sound, like it's a lot of bragging there. It's related for infrastructure maintenance. So we have 2 robots now in the Sydney Harbour Bridge, one painting the structure, and the other one is inside this kind of inner structure of the hardware. It's inspecting and monitoring the condition. So this robot in particular was designed in-house, and it crawls inside the bridge and goes autonomously, inspects that there are no corrosion, or if there is corrosion, points it out, and this is all communicated to users and things like that. So we also have a big collaboration with Sydney Water. We've been working with Sydney Water for the last 7-8 years. Now we have a robot that is deployed in Sydney Water. Every time there is a break in the pipes, in the water pipes, the robot comes in and inspects the condition of the pipe, and it's currently operating in the Sydney Water. And well, we also work in the automated container terminal. Yeah, but that's an oldie but goodie. So that's related to infrastructure maintenance. Those were the projects, but we also have lots of projects with assistive robotics, trying to help patients to transfer, for instance, moving around with our smart hoist, or a robotic co-worker. So this is a robot that helps to do grid blasting tasks. Obviously, the robot gets all the tasks and the user just do the fine manipulation. We have also projects. We have a large industry collaboration with MLA, with Midlife Livestock Australia, where we're looking at, well, analyzing and yield for beef and lamb, and other projects with Downer for in the rain transport, like for analyzing when people, how many people are in the train station, things like that, to optimize the when people are boarding the trains. So overall, our robots, we have a wide variety of robots, or a lot of robots in the field. Yeah, you can see our climbing robots, a device in the abattoir, and yeah, some other robots in the pipes, some other types of robots. All right, so now I'm going to talk about the recent work that I'm here today to talk to you about. I'm going to start with something that we call Gaussian Preintegration. And let me just motivate it a little bit. And I have to apologize, as I'm gonna be bothering you with some of equations. Hopefully not too annoying, but I think to introduce this topic, it just works well if we put the equations here. So just inertial systems, or inertial aided systems, allow like fast perception and estimation. And for instance, a visual inertial system gives a monocular only camera, for instance, the ability to have a scale, for instance, and allows this very dynamic motion go faster. So for instance, in drones, it's very well utilized. LiDAR inertial systems also are pretty good in the sense that the inertial information allows to distort, for instance, the rotating LiDAR, the motion distortion of rotating LiDARs. And some of this framework on this, I'm going to talk about it today. But the most important part that I want to highlight here is that it's all based on inertial. And inertial IMU systems have these challenges in terms of when they are combined with other sensors. Well, we get asynchronous measurements, right? IMU goes, it's I don't know, 100 hertz. Well, the cameras go 30 frames per second. Obviously, we have this multi-sensor time shift, and we need a string-set calibration. Also, to recover the biases of the IMU, we need we need excitation on all axes, and that doesn't necessarily goes well, for instance, with the front end of LiDAR-based perception. So there are many challenges that we need to tackle with these systems, but obviously there are lots of pros that this kind of system give you. So let me go to now our first set of equations. This is just to present a dynamic system, right? Like we have the derivative of our rotation is equal to the rotation times the angular velocity. And same for linear velocity, is the derivative of the linear velocity is the acceleration. I mean, this is well known, and the derivative of the position is the velocity. So what I want to point out here is just the integration, right? Which is what we need when we get inertial measurements. So we need to integrate measurements because we receive, for instance, angular velocities and angular accelerations from gyroscopes and accelerometers. So a typical integration will be of this shape. Something that I want to highlight more than the equations, this is a standard integration, nothing new here. It's that this integration depends on the initial conditions, on the initial orientation specifically. So a few years ago, around 2010, 11, or 12, well, 12 is the journal paper, Lupton came up with something called pre-integration. And people who have been using visual inertial systems should be very familiar with this concept, because now it's kind of the way to go when using visual inertial integration. The key idea of the pre-integration is that you decouple the initial orientation from the gyroscope measurements. And then if this orientation is decoupled, you can generate these pseudo measurements, or these pre-integrated measurements, which is delta R, delta B, and delta P, by decoupling from the initial condition. Yeah, so you can integrate these measurements from time 1 to time t. So to time 1 to time another time. So hopefully this is clear. So the main idea is when you have a system like a visual inertial where your frame rate it's 30 frames per second, and you want to include all the IMU information between frame and frame, you could simply integrate that independently of how the initial condition was. And this is very well utilized, allows us to put together multiple observations of the IMU in a single frame. Okay, so what I'm going to present today, it's following this pre-integration work, I'm going to present what we call Gaussian Preintegration, where we use, it's a continuous and probabilistic pre-integration method, which is based on Gaussian processes and linear operators on kernels, yeah, which allow to do analytical integration. And I'll go through that in a minute. So our pre-integrated measurements, or what we call the Gaussian pre-integrated measurements, are a set of similar to the pre-integrated measurements that we had in the from Lupton's and Foster's paper, but that are computed slightly different, right? So the standard pre-integration uses numerical integration. In this case, we're gonna use analytical integration through the kernels of the Gaussian process. So just a quick recap, hopefully everybody is familiar with Gaussian processes. So a Gaussian process, you can see it as a distribution over function, right? So if you have a set of discrete measurements that of a function, you can, using Gaussian processes, you could find a function with its uncertainty, the function that underlines these measurements, right? So imagine these are your IMU measurements, probably less continuous, but you have a bunch of discrete measurements. You could find a function which is non-parametric that follows these measurements, right? And filters some noise. So this is here, this what we call Gaussian process with zero mean and some kernel function. And so this allows us to do probabilistic, data-driven probabilistic inference, meaning we can query points at any time. And this is, and here I'm talking about a times, a signal that it has in the x-axis a time. And for instance, in the y-axis, you have acceleration in x, or acceleration in y. So I want this signal. So as I said, you could, with this definition using the Gaussian processes, you could query at any position, or at any time you can query the value of this function. Yeah, and the key thing is that you use a kernel function to learn the correlation. All right, so let's talk about how do we use this for the Gaussian process pre-integrated, the Gaussian pre-integrated measurements. So we have to make a differentiation for rotations. In this case, rotation have two cases. So the case when you have one axis rotation, so for instance, a robot driving on a 2D plane will have only one axis rotation. So in that case, it's a very, it becomes a very nice case because you could do analytical integration directly in one axis. However, if you have motion in the whole space, like the rotation is in the 3 axes, then you cannot use analytical integration, and we have a special case for that. But let's say we have one rotation axis, so we can follow a very nice approach to generate these pre-integrated measurements. So we have, I don't know if you guys are familiar with the concept of linear operators. So Sarka talks about it, or discusses this in combination with Gaussian processes. So if you apply a linear operation to a Gaussian process, it's still a Gaussian process. So it produces another Gaussian process, and that's a great a great property to have, because a linear operator here, we are talking about, for instance, integration or differentiation. And this very powerful property allows us to do analytical integration of a kernel, for instance, that we could integrate. So if we talk about the square exponential kernel, you could analytically integrate this kernel and immediately get the analytical integration of the function that you are trying to estimate. So, and this is just notation, right? So this is what we call the linear operation over our angular velocities in one axis. Our angular velocity is defined as a Gaussian process. We apply a linear operation, and then we can get the integral through inference in the exact same way we get the interpolation of the points on the function. In exactly the same way, we can also get the integral of this function. And well, this is great. So then we have analytical integration just through the kernel of our function, of our underlying function. Then, so that was rotation. We can do the same for velocities and positions, right? So the only key thing is that first you have to project the accelerometer readings into T1, and that's done through the through the delta rotation that we calculated as part of the rotation measurement. So if we define our Gaussian process, the accelerometer already projected at time T1 as our Gaussian process, then we can do exactly the same, integrate, apply our linear operator to the kernel and get our integrated measurements. So that brings us to the overview of our Gaussian process pre-integrated measurements. So we have gyroscope readings. We fit the Gaussian process to them. If it's one axis rotation, we can integrate analytically, to get our measurement, our continuous and probabilistic measurement, then project it into T1, and then integrate again to get the delta V and delta P, the linear velocity and position of of the pre-integrated measurements, right? Okay, so if it's not one axis rotation, then it's not as nice, right? It's not analytical integration. You simply, what we do is very simple Gaussian process inference, and then we do numerical integration on the query angular velocities and get our pre-integrated measurement and project again. All right, so just how does it look like in comparison with for zero order interpolation, right? So this is zero order interpolation. This is linear interpolation. This is the type of, this is a very commonly used type of interpolation. And this is our Gaussian process interpolation, based interpolation. So this is the function, right? And this is the integral. So you could see it starts deviating from, even for the linear approximation, starts deviating the integral. While in the Gaussian process, it follows very nicely. So we did some comparison with linear interpolation, with using Gaussian processes and then interpolating, and well, the GPM becomes much more accurate. And this was something we presented, we published in RAL this year. So with these measurements, we proposed two frameworks. I mean, we use this type of measure, Gaussian interpolated, pre-integrated measurements in two different frameworks, and that's what I'm going to talk about it now. So IntoLama. IntoLama is an inertial LiDAR localization, auto calibration, and mapping approach. Why we have another approach that does inertial LiDAR integration? Well, it's there at the time when we started working on this, there were no that many, but anyway, there was still something out there. Our main claim is that we tackled the motion distortion of the rotating LiDARs. Obviously, for solid state LiDARs, well, that's a different story. But well, we still have lots of these ones, so it's an important issue when you have that you have in rotating LiDARs. So a classical approach will use the LiDAR scans, at 10 Hertz, and it will get it will get constant velocity, assuming constant velocity over a whole scan, and that's how they kind of most of the approaches tackle this motion distortion. But it's not that accurate, and especially when you have very dynamic motion, it doesn't. This assumption of constant velocity during the scans is not very good. So what we do instead is we use each LiDAR point as a measurement. Not exactly that, but that's the whole idea. So we have LiDAR points at 300 kilohertz. So this is way faster than what an IMU could give you. So then we use our Gaussian process, Gaussian preintegrated measurements to constrain for the point position in the scan to be constrained with this Gaussian process preintegrated measurement. So you can see now we need to upsample our normal. Besides integrating, that's one thing, but we also need to upsample our measurements, our IMU measurements, to cater for the high frequency of the LiDAR points. And then, well, we use we recompute our features as I'll present in a second. But this is kind of an overall frame. What's IntoLama, or how IntoLama uses the Gaussian process, the Gaussian preintegrated measurement. So we have this full batch offline optimization based on factor graphs. That's pretty standard. We use a maximum likelihood estimation, so everything is probabilistic. It is a tight integration, like the inertial and LiDAR measurements are tightly integrated, and we estimate poses, velocities, IMU biases, time shift, and extrinsic calibration, all in the same framework. So you can see here in this figure, so we have the time one at the LiDAR scans. Then we have a bunch of LiDAR points, which is our 300 kilohertz sensor. And we calculate the poses of the IMU at the time of the start of the scan. So our LiDAR factors are very standard, like point to plane and point to line. This is, if you are familiar with LiDAR-based localization and mapping algorithms, Loam, for instance, that he will use similar features to ours. But in this case, we use Gaussian preintegrated measurements per point to correct for motion distortion in each scan. Then we have the IMU factors that constrain position and velocities from scan to scan, and then we also estimate the bias and time shifts. So we have the LiDAR, we group it into frames, which are not, as we'll see later, they are not exactly the same frames as, let me go back to you on this one. So it's, we are not using the 360 rotation only as frames, but we'll see that. Then we use the IMU measurements. We calculate our Gaussian preintegrated measurements. we use them to in the computation of our feature location, and we use them as well to constrain our LiDAR factor. Yeah, and then we push it all on the optimization. A key thing from IntoLama is that we recompute. Once we recompute the state, we can recompute the features. So then the better estimation allows us to have better a better front end. Yeah? So it's kind of back and forth computation of features. So just in the LiDAR factor kind of visualization, we have this the position of the IMU at the start of the LiDAR scan, and then we have a bunch of factors that connect scan to scan, which are the IMU factors, some LiDAR factors, the biases, and then we have a time shift that relates to the to the time shift between sensors, which we need here, and also in this embedded in all the equations, we have the extrinsic calibration, which we also estimate. And then we can have, for instance, loop closures, which will be only a LiDAR factor here, not the IMU constraints, for instance. So overall, our cost function, MLE, standard MLE, so we have, for the LiDAR factors, we have point to line and point to plane distances that are being minimized. The intershift constraint between sensors, the biases, these two, and the IMU factors. So we use the standard treatment for biases and time shift, which is like just simple first Taylor order expansion. So the front end, as I mentioned, we have points that belong to planes and points that belong to lines, which are corner points and plane points. We, as I tried to explain before, but I'm not very well, and this image is going to help me to explain it better. So we don't use a full 360-degree scan. We actually assume, because we are using independent points, we can decide how big is, or how small, or how short is, how large or how short is our scan. So we actually experimented of using longer, larger at 360-degree scan with association of features from both sides. So in this, like in this case, and that gives us a lot of much better constraints, as you could see here, to do the data association, and give us pretty good results. Like this, we get very nice maps from indoors. This is a data set that we took inside the UTS space offices from people who have been there, maybe Thierry, you know, I can tell you my office is this one. But yeah, this is a big area where some PhD students sit over here. There's a bunch of offices here, and we only use IMU and LiDAR. Cedric, who is the student who's been working on this for a long time, he was carrying the sensor around, moving it, and reconstruct this with IntoLama. So we have some comparison with LOM, which is LiDAR, odometry, and mapping. It's very well known. Okay, this is not fair because LOM is real time. Our approach is completely offline. But still, we can get very accurate maps in comparison to other approaches. And yeah, this is our previous approach where it didn't have the auto calibration and the IMU factors. And we were not using the GPMs, which we were just using Gaussian process for upsampling, but numerical integration. Well, in IntoLama, yeah, we push for the GPM. So in outdoor space, we have also nice, we get pretty nice map. This is just the Koblenz-Landau campus datasets from MC2 SLAM. So we cannot use all the datasets because we need the timestamp per point. The standard ROS driver for the Velodynes and most of the 3D LiDAR do not provide that. So we need, yeah, so we couldn't test in Kitty or something like that because of this request. You could potentially come up with something to get those timestamps, but it will follow, for instance, a constant velocity approximation or something like that, which at the end defeats the purpose. So we found a data set from people who work on MC2 SLAM, which actually provides a timestamp per LiDAR. And we are using a driver that was developed actually by James Underwood in ACFR. Okay, so moving on, and I have to see how we're doing on time. I think I'm running out of my 40 minutes. Sorry, Thierry, I'm very slow. All right, so I'm gonna go quickly from now. So we apply something. We also use the GPMs for event-based cameras, right? And I think you guys are more familiar with event-based cameras, where you have it's a set of events, a synchronous stream of events that are gives you XY coordinates in the space, some timestamp and some polarity, which we don't use, but it gives you this trigger events upon a change of intensity, right? Like due to motion, mostly either the camera or the what it's looking at. So there are many pros. This has high temporal resolution, very high dynamics range, low bandwidth, and it's a natural hardware edge detector. But there are many challenges, right? Like the events are asynchronous. There is no information, little image information. I mean, you have to work through it to get that image information. So we proposed event-based visual inertial odometry based on lines, which is it's a full batch optimization. It's very similar to IntoLama. It uses the same factor graph. Maximum likelihood estimation. We type the events and the inertial, and we integrate it tightly, and we estimate poses, velocities, ion biases, and 3D lines. So this is slightly different, right? Like, and that slightly different treatment. So we have an IMU factor that allows us to characterize this continuous motion using GPMs. And we use event to line distance and some line extremity management factors that are all part of idle. So, and the line extraction is based on clustering. So we cluster lines, we generate our Gaussian Preintegrator measurements and use that to constrain our lines and then do graph optimization. So in the front-end bait, we have some, yeah, like this is the image not used, but we have the XY positions and the timestamp of that event. We assume that there are line structures in the environment, and they represent like local patches, local planar patches in the spatio-temporal representation. So if you could see these lines, when you get the set of events, they look more like planes in this space X, Y, Z, and T representation. Sorry, X, Y, and T representation. So you get these kind of patches. So we exploit that. So to do this event to line association, we cluster these planar sections, yeah, and obviously, yeah, and classify them, and that will represent one line in the image. Each cluster will be one line in the image, and that's what we exploit in the front-end bit. Then in the back end, as I previously, as IntoLama does, it's similar formulation, but the event factors contain, well, the event to line distances and some repulsion and attraction forces. That's how we call it, just to manage when a line becomes bigger or smaller. And we again use series for nonlinear least square optimization. So this is what I was saying. So if we have this is our line, these green dots are our extremities. We have points outside. We apply this repulsion factor that allows us to move our extremity. And also we have some attraction force for the ones that are inside our line, right? And this allows us to estimate, to do pose estimation in very dynamic motion. And you can see, well, so let me just put it again. So these are the X, Y, Z position. It's probably very small to see. These are the velocities, and these are the, oops, again, these are the orientations. And we have a very reasonable results to be a event-based camera pose estimation. And you can see the reprojected lines in the image. So compared to Rovio or Rovio plus MapLab, which is also based on optimization. So Rovio is filtering, so it's slightly different, but we do a good job. I mean, obviously Rovio and Rovio with MapLab, they are using the image, which it is more accurate. That there is nothing we can do about it. But the idea of this framework was as a proof of concept, that we could estimate the poses using this approach. And yeah, like most of an orientation, this does pretty well. It's translation, what there is a little, yeah, I think that needs some improvement, but as a proof of concept works pretty well. So my last topic, and hopefully won't take me too long, because I'm think over time. It's about a very recent work that we just submitted to RILE. It's in archive, so if you want to have a look at the paper, it's already there. It's the logarithmic Gaussian or the log Gaussian implicit surfaces. So this is a slightly off topic. We are here. What we are trying to do is mapping. To create a mapping, continuous and probabilistic mapping and planning representation, right? Using Euclidean distance field and implicit surface. So just as a quick example, this is how Euclidean distance field look like in a 2D map. So the closer you are to the surface, the distance becomes smaller and smaller. And it's the Euclidean distance field is like the distance from every single point of the space to the surface, right? obviously following the normals, which is the minimum distance. That's slightly different to the TSDF, which is a very common mapping representation, right? Where you use the sensor's locations and you go through the sensor location to the surface. And it's an excellent representation for implicit surface, so you can recover the surface very accurately, but it's not a good representation for the distance field. Yeah. So if you want to use this for navigation, the truncated, you have to apply some post-processing to the TSDF to be able to use it as a Euclidean distance to the nearest object. All right, so the Euclidean, this is just the definition, right? So if you have any point in the outside the surface, the distance field has to take you to the surface through the normals, which will be the minimum distance. This is, so if we consider a scenario where S is a manifold, yeah, so this S is our manifold, then there is the O'Connell equation, which defines this kind of how this distance field dilates along its normal direction with unit speed. Yeah, this is a very well-known definition, like using the O'Connell equation, the partial differential equation, to describe the distance field. And well, the purpose of this work is to actually estimate this distance field, given a bunch of discrete measurements, and reconstruct at the same time the surface. The problem with the O'Connell equation, if we want to solve it to recover the distance field, is like it's nonlinear and how to solve. So there are combinatorial approaches and like mainly numerical approaches to solve it. So we look at what people have done in the computer graphics community to tackle this problem of the O'Connell equation of being easy to solve. And there is a paper in 2012 that talks about the geodesics in heat, which is pretty much what it's saying. What it proposes is that you can simplify the O'Connell equation, that you can approximate the O'Connell equation with a linear equation, which is the Screen-Poisson equation, to be able to get, in this case, the distance on the manifold, meaning on the surface, the minimum distance from one point to any of the points. And this is defined on the manifold, on the surface of the object, right? So this is here. Yeah, but it's a very nicely defined. This heat kernel, which is the what allows us to simplify the distance function, has a relationship with the distance in this way. Yeah, so the relationship between the distance and the heat kernel had this relationship. So then the approximation of our distance, which will be u, will have this form that it's proportional to the logarithmic of the heat kernel. And then obviously you can compute the heat kernel using the exponential. So this is, as I said, defined on the manifold, but in our paper, we present of a very simple treatment to apply it to outside the manifold, which is what we want. We want the Euclidean distance from any point in the space to the manifold. And it turns out to be very simple because the boundary conditions are the same. The only downside with this approach is we lose the sign. So usually TSDF, for instance, is this sign distance function to the surface. So you can tell what's inside the surface and what's outside the surface. In our case, following this approximation, we lose that sign. This can be recovered in a different way, but we're not going to talk about it now. Okay, so Gaussian process. Again, we use Gaussian processes. These are very well known and utilized. I believe Thierry has used as well Gaussian process implicit surfaces, which is obviously the idea is to model the function, the implicit function, with a Gaussian process. Well, there are not going to get too much into it, but you could also, so when TSDF, you need to have, for instance, points inside the surface and outside the surface to be able to get the implicit surface. With Gaussian process implicit surface, you can also use the derivatives or the linear operators that we saw with the integrals. You can use the different, the derivative or the differentiable operator to be able to get the normals of the surface. So you just don't require points outside the surface or inside the surface. You only require the normals of the surface to get a continuous representation of the field. So what we propose is to not to model the function itself as a Gaussian process. So here, for instance, we have a set of these 3D points in the environment, right? So that's what our sensor gives us. For instance, a LiDAR or a 3D camera gives us 3D points on the surface. So in this case, you put for your Gaussian process modeling, you use the points on the surface are equal to 0. In our case, we propose to use, following the result that I presented before for the approximation of the distance, we propose to use the target measurements to be equal to 1. And then the distance is given by the logarithmic of the function that we are approximating. And it turns out like that there is a nice, and sorry, this is not our result, but turns out that there is a nice, the white Vidal kernel actually satisfies exactly the screen Poisson equation, which is, well, the one in here, sorry, the one in here. So Gaussian processes were very well suited for this. So in our log GPIS, we have the point clouds, we have a pose, we model our distance field and implicit surface through the log of the GPIS, and then we can get visualization and planning. So if you see here, this is the standard GPIS that doesn't have the log, where you could see that points far away from the surface, because you can, something that it's important here to highlight is that points on the surface are our measurements. Everything else, well, it has to be made up by our Gaussian process implicit surface, right? So points that are far away from the surface, there are points that we haven't observed. The Gaussian process doesn't do a good job to infer the distance. Well, using this simple trick, or following the approximation of the kernel equation through the screen Poisson equation, you can actually get the recover very well. All right, so I'm gonna finish here. Like, this is just results of what we have of this, of how we recover the 3D surface and the distance field using this log GPIS. And I finished. Sorry, Thierry. I know I'm very well over time. But yeah, so these are just results, acknowledgement to my PhD students working in these 2 topics or 3 topics, and some collaborators that have been involved in this work. Yeah. Thanks.
Yes, thanks, Teresa. Big round of applause all around, I'm sure, virtually. That's really good work. I will take time maybe for a couple of quick questions. We have run slightly over time, but got to see that most people hang in there, so that's good. That's a good sign. Any questions online? You can also put them in the chat if you prefer to formulate that there, and I can give the the questions for you, Peter.
Teresa, thank you. Just going back to some of the earlier stuff when you're using the Gaussian process to improve the quality of your inertial sensor integration.
Yep.
What's the time hit for doing that, and how do you choose the parameters of your Gaussian?
Yeah. So we actually, for that,
GP.
I mean, there is nothing. Yeah, there is nothing that shows this, but essentially we use a window. Yeah. And we do train the hyperparameters in the window. But remember, this is an offline mapping, right?
Yeah, sure.
So we just live with that. It is a bit expensive, but given they are 1D signals, right? And we use a time window, right?
Mm-hmm.
So training is not that hard. It's still on cubic, but it's feasible because we are using short time windows.
Okay, thank you.
There's a question from someone online. Thanks for the great talk. Referring to the first part of your presentation, if I am correct, you use GPs to interpolate IMU measurements at the timestamp of your choice, where you don't have an IMU measurement. And then you do IMU pre-integration on this interpolated upsampled measurement. Have you tried modeling the IMU state instead of IMU measurements as GPs?
Yeah, I haven't, but that's that's work that people have done on continuous state estimation, modeling the state as continuous state. So yeah, it's not our approach is different. Because that continuous state might allow you to do, in our view, the continuous interpolated measurements allows us to do the distortion, right? And that's the main purpose of it, right? Not to estimate continuously the state over time. We're still using discrete state. And that's it's a different approach.
I can ask questions, I think. Just to give the event-based camera application, though you mentioned that you assume that the lines that you're capturing are planar, and obviously they are in the test you're making, which is fair enough. I guess obviously the question is if they are not, what happens and do you have any ability to know that or to filter that out?
It's more than assuming that the lines are planar. It's like what we're saying is that line segments in the image are planes in the spatial temporal space. Yeah, so it's a different thing. So there might be other features that are not lines, which are not going to be planes in the spatial temporal, but these are lines on the 2D plane that are show themselves as planes in the spatial temporal space.
Okay. So you're testing that as you process in your algorithm, you're testing that they are actually planar.
Yeah.
Yeah. Okay. All right. Good. If there is no last questions, I was looking at the chat, no raised hands. Last chance for a question to Teresa. Otherwise, we'll gonna go for lunch. Thanks a lot.
Sorry to delay your lunch.
No, that's okay. That was really good work. Really glad to see that. That's very good stuff. We'll probably take a bit of time to absorb the math, but it's definitely something looking to further. It's good. I mean, it's good to see. It's really good work. Thanks again for the talk and yeah. Well, on behalf of everyone, I'm doing the clapping. It's not as noisy as it would be in real, but I'm sure we will come up with better ways to do that.
Yeah. Now, thanks for inviting me.
Thanks, Teresa, and see